Welcome to Lesson 7C, Temperature Inversion, Absorbing Ground, Part 1. We're still talking about Gaussian plumes, but now we're going to add a temperature inversion, and we're going to start with an absorbing ground. That's typically the easiest. Let's look at several cases here. The first case is a ground-based temperature inversion with the stack above the top of the inversion. So here's a diagram. We have a temperature inversion that's ground-based. So here's the temperature inversion. And then it becomes unstable out this way above the temperature inversion, the top of the ground-based temperature inversion. We're going to call that height HT. And the height where the source is, including both the stack height and the buoyancy, like we always do, is H. So we see that in this case, H is greater than HT. So as I say here, the stack height with the plume higher in elevation than the top of the inversion. This whole region above the temperature inversion is unstable because it's this large lapse rate here. We have a negative lapse rate. We have a temperature increasing from the ground up to the top of the temperature inversion because that's the definition of a temperature inversion. And remember, when you have a temperature inversion, nothing can penetrate into that temperature inversion because it's kind of like a lid. And this is stable. I'll use blue for stable, keeping with my coloring convention from previously, inside the temperature inversion. So what happens? Well, the plume comes out, and we're looking at an unstable situation, so this might be a class A or B. Remember, those are the most unstable. It spreads, and it hits the top of the temperature inversion, and then it's kind of flat. So this is a lofting plume, and for this case one, the plume theoretically never hits the ground because it can't penetrate that temperature inversion. Now in real life, eventually it'll hit that miles and miles downstream, but by then the plume is so diffused that it doesn't cause any harm to people on the ground. So in this case, the Gaussian plume model isn't even necessary if all you care about is ground calculations. You're never going to have a hazardous area down there. So this case is trivial. If I gave you a homework problem or a quiz question with this kind of a case, where's the hazardous area? Your answer would be there is none. Okay, let's get something more significant then. What about a ground-based temperature inversion with the source below the top of the inversion? So we have the same temperature inversion that we had in the previous case. This is now case 2. And the difference here is that we have a short stack and not much buoyancy, such that in this case, H is less than HT. Remember, H is where the source is, and HT is the height to the top of this ground-based temperature inversion. How do we deal with that? Well, if you look back at the Martin model, remember that class F was the most stable, class A was the least stable or the most unstable. So we're going to just use class F as the most stable case when there's a temperature inversion. And then remember from previously, we call this a fanning plume. So it spreads rapidly horizontally, but not very much vertically. But it does spread. This is stable inside the temperature inversion, and the plume is entirely within the temperature inversion. It's pretty stable, but it does spread somewhat. And if you go far enough downstream, this thing is going to hit the ground eventually. We don't have to worry about it, but we can apply our equations and see if it ever does hit the ground and cause any hazardous area. Think about this case where we go really far downstream. So we go downwind in the X direction, really far. And one of two things happens first. Number one, the bottom of the plume will eventually hit the ground. Or number two, the top of the plume eventually passes through the temperature inversion. So let's consider the first case. Let me label a few things. Now, we always assume that the plume spreads the same amount vertically up or down. So it's spreading the same amount this way as this way. And we're looking from very far away. This is a fanning plume. Remember, we called XG where the plume hits the ground. And in that case, we know that that has to be where this center line of the plume to the ground is H, and then it's also H up, since H is the distance to the source. And so as that comes down and reaches the ground, that's a capital H there. This happens when HT is greater than 2H. In other words, this case 1 that we're calling it can only happen when HT, the top of the temperature inversion, is greater than 2H, just from geometry there. So how do we analyze this one? The analysis is exactly the same as previously, so we don't need to really do anything different. different. If you already have your computer file set up in Excel or MATLAB or whatever you're using, you don't need to modify anything from how you've done these problems before. We can plot a hazardous area. We can calculate CJ as a function of X at a certain elevation on the ground, whatever we want, just like we've done before. The only difference is that we're going to use class F, so you'll have to change your A, B, C, D, etc. And that's all there is to it. So we're not learning anything new here. The top of the plume will hit the top of the ground-based temperature inversion. That's not going to happen for a long time. Okay, now let's look at the second case where the top of the plume eventually passes through the temperature inversion. So what happens there? In this case, we're going to look at the situation where HT is less than 2H. So by the time this thing spreads to 2H, where this is H, and again, this is H here, just from the plume spreading, it has already passed through the temperature inversion. So once it goes through that temperature inversion, the smoke is kind of limited. It's very stable inside, but once it passes through there and diffuses into it, it starts becoming unstable. So what happens to the plume? Well, the plume starts to grow more rapidly here because this is unstable out here. So it's a fanning plume here, and then it becomes a lofting plume here. You'd have different coefficients and everything. But what I did was plot CJ as a function of Z, as we're typically doing. And what you can see is, as long as everything's within this temperature inversion, CJ is symmetric. As soon as it crosses that temperature inversion, however, it becomes unstable and it mixes much more rapidly. So the plume diffuses, you have this really long tail. So now the Gaussian is no longer a Gaussian. In fact, it's skewed. It has this long tail. So we really cannot use a Gaussian plume up in this region. However, this bottom portion doesn't change at all from what we had before. Just because it's changing out here, this is way up here up in the atmosphere. So things on the ground don't change. So compared to this case, we said that our analysis is the same as previously, and we can say exactly the same thing here then. So we don't care what happens above the temperature inversion. That doesn't affect conditions on the ground. Now this plume is eventually going to hit the ground and you'll start to get some kind of a hazardous area way downwind here. But it's already hit the top, but that's distorting the plume shape on top. It's no longer a Gaussian, but we don't care. So our analysis as far as the ground level is concerned, or a little bit above the ground, the nose level if you want to deal with that, we use the same model, same equations. All we do is set the class to F. So this really isn't anything new again, even though this temperature inversion is there. So here's the bottom line. If we're concerned about concentrations at or near the ground, we still use the same equations as previously with class F. We'll always use class F when there's a temperature inversion, whether HT is less than 2H or greater than 2H. So either of these cases, these scenarios, far downwind, we're going to use class F and the same analysis as we did before. So let's do an example problem. Chemical plant emits a gaseous air pollutant. I'm going to use pretty much the same numbers as our example that we've been using all along here. I just picked these kind of at random and I keep using them. So we still have 80 and 20, and our capital H is then the addition of those, so 100 meters. I did change the U. It turns out that you typically have these fanning plumes and temperature inversions when the wind speed is less than about 3 meters per second. So I changed that. We still have the same m.js as before in our previous examples, so we can do some comparisons. Now the atmospheric conditions have changed. This is very early in the morning with few clouds, very few clouds. A ground-based temperature inversion. Anytime we have a temperature inversion, we use class F. Top of the temperature inversion is way up there. So we just want to make sure that the H is less than HT. That's our requirement, so that our plume is entirely within this temperature inversion. So it is a fanning plume. And then we don't really care how high that ground-based temperature inversion is because of those two cases I just looked at, those two scenarios. We have an absorbing ground. We'll talk about reflecting ground later in another lesson. And the PEL is the same as before. So the only thing I changed was that it has a temperature inversion and I had to lower the velocity. I could have kept that speed the same just for illustrative purposes, but I lowered it to be more consistent with real life. And we want to do the same things we've done before. Plot mass concentration as a function of X directly downwind, and plot the hazardous area at ground level downstream of the stack. So remember, that means Z equals 0, and directly downwind means Y equals 0. So that's the center line of the plume. And here we're going to look at the variation horizontally in the y direction to calculate the hazardous area. I want to just go back to this stability classification table of the Martin model that we've talked about before. We keep using this for all our problems. And notice the only places you see F are these two places. Remember, F is the most stable situation. And this says nighttime, but nighttime can extend to very early morning. So just after nighttime, this is still valid. And the speed has to be less than 3 meters per second. And it has to be clear. You can't have a lot of clouds. And so in this case, we are right here because we have a speed of 2.85 meters per second wind speed, and we have clear early morning temperature inversion. So again, anytime we have a temperature inversion, you don't really need to look at this anymore. You just say, oh, if my plume is inside the temperature inversion, which it is in this case, as long as H is less than HT for a ground-based temperature inversion, it's a fanning plume, and we use class F. So that's the first thing. I make a statement for this course, and this is important if you're doing any homework, quizzes, final exam. Always use class F, the most stable case, when the plume is inside a temperature inversion, since F is the most stable Martin case that we have classification. The plume does eventually hit the ground, and so the analysis is the same as previously to plot the hazardous area just like we did before. So you don't have to really change anything except those coefficients A, B, C, D, and F for class F. So for this particular case, again, we're just doing the same problem we did before, except now it's a fanning plume, class F. So I used the same exact spreadsheet that I had been using for all these examples. All I did was go on top where I have my A, B, and C, etc., and change those. I also had to play around with the range of X here to make sure I have a nice looking plot. And here's my results. So you can see we barely go above the PEL. This is again the absorbing ground. I'm plotting the PEL here, which is 50. And if you had a slightly smaller m.js, you could have a case where this curve never even reaches the PEL. And why is that? It's because since it's fanning plume and it's spreading so slowly in the vertical direction, you're going to go many, many kilometers downstream before this thing hits the ground. And by then it has spread laterally in and out of the page here in the Y direction significantly before it hits the ground. So it has a chance to diffuse quite a bit, even though it's not diffusing much in the vertical direction. It is diffusing a lot in the horizontal direction as you go farther and farther downstream. So in this particular case, you can see that we do reach the hazardous zone here at roughly 11 kilometers, which is much further downstream than we had before if you look back at our previous couple modules, and it goes up to about 19 kilometers. And then I actually plotted that hazardous area, everything inside this ellipse. This one looks sort of like a egg, vertically a squashed egg, because I have such a huge scale in X. And then for comparison, if you look back at the previous example where we had the same plume, but we had no temperature inversion, it was a class D, has been my example for many other of our lessons, we had this hazardous area. So if you look back on this plot, it would look something like I sketched here in blue. This is the hazardous area for our previous example with an absorbing ground and a class D conditions. And this extends all the way to 250 meters. You may remember those numbers, the negative 250 meters for that problem. And the extent in the X direction was from about 1.5 kilometers is where the hazardous zone started, and it went to about 7.5 kilometers. So one important takeaway from this is that the hazardous area is much farther downwind than the previous example, and the area is actually smaller. You take the area of this whole thing, it's smaller than the area of the blue one there. In other words, it's less hazardous, but there still is a hazardous area. There still can be downwind of a plume in a temperature inversion because that plume does eventually hit the ground. In this case, it's really far downstream, and this doesn't happen till about 11 kilometers and extends till about 19 kilometers. So that's pretty far downwind, but then you can still have this hazardous area. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.